Hello everyone, this is Dr. Gallenstein and thank you for joining me again. Today in this lecture, I will be going through the experimental approach to development economics. Alright, I will be talking about something that we call RCTs, or randomized controlled trials, a little bit about how to design them, and then a little bit about how to analyze data that would come from an RCT. All right, but before we begin, let me do a brief refresher, a brief review from our last lecture, just to get us started for this lecture. Okay, so in our last lecture, we introduced this issue of wanting to assess the impact of a development program. And specifically, when we say the impact, we want to know the causal effect. We want to know the effect that the development intervention is having on whatever outcome we want to study. So the example that I've gone back to again and again is, let's say that we want to raise farmers' incomes, and we come up with an intervention where we're going to give them fertilizer. And we want to know, okay, what is the effect of giving fertilizer to farmers on farmers' incomes? All right, so their incomes is the outcome variable, and the intervention or the treatment is the fertilizer, okay? And so we were talking about, we want to identify the impact of the development program. All right, but then we talked about this problem of causal inference. We talked about the problem of causal inference. So what we said is that if we want to know the effect of something, what we would want is to compare what happens to people when they get the intervention to what would have happened to them if they had not gotten the intervention. All right, but then we said that our problem is that we're never able to observe the same person at the same time, both with and without the intervention. So we can't observe causation. So we have a problem. The problem here is that we don't have the true counterfactual. The counterfactual is, if you remember, the counterfactual is what would have happened to someone that got the intervention if they had not gotten the intervention. What would have happened if they had not gotten the intervention? The same person at the same time. That's the counterfactual. We don't have the true counterfactual because we can never observe the same person at the same time with and without the intervention. All right, so then we went on to say, okay, if we can't observe causation because we don't have the true counterfactual, what we went on to say is that, okay, we will estimate it. We will estimate the causal effect. And the way we do that is we take people that have the intervention and we compare them to people that don't have the intervention. We say the people that have the intervention, that's the treatment group, and the people that don't have the intervention, that is the control group. So basically, we're using this control group, this group of people that doesn't have the intervention, we're using those people as a counterfactual. The question is it a valid counterfactual? Is this control group a valid counterfactual? So then we went on to say, okay, if there is some reason why the treatment group has the intervention and the control group doesn't, then we're going to have selection bias. And if we have selection bias, then that control group is not a valid counterfactual, which means whatever estimate we get of the treatment effect is going to be wrong. It's going to be biased. All right. And so we have this problem of selection bias. And where I left off in the last lecture is, what do we do to solve the selection bias? How do we solve it? How do we get rid of selection bias? How can we say that selection bias is zero? How can we say that there's no selection bias? We want to be able to say there's no selection bias. We want to be able to say there's no selection bias so that we can identify, we can figure out the real causal effect of our intervention. How do we do that? Today, we answer that question, and we will jump right in. So the answer to the question is randomization. And let me be more specific. What the answer to the question is, if we can randomly determine who gets the intervention and who does not get the intervention, then we can conclude that there's no selection bias. All right, now let's take an example. Let's say we have a sample population of 1,000 farmers. What I'm saying is, if I can randomly select which ones of those 1,000 farmers, which farmers of those 1,000 get the intervention, if I can randomly determine it, if I can randomly assign who gets the intervention, then I compare the treatment group to the control group, and I can say that there is no selection bias. All right, so if it's randomly assigned, so let's say I've got 1,000 farmers, I randomly pick 500. When I say random, I mean there's nothing that determines whether or not I get them or not. It's totally random. Randomly pick 500. Then I will compare the incomes of those 500 to the incomes of the 500 that don't get the treatment. All right, so I randomly pick 500, give those 500 the treatment. The other 500 don't get the treatment. They don't get the intervention. Then I compare the incomes for the people in the treatment group to the people in the control group. I compare the incomes for the people that got the intervention to the people that didn't get the intervention. And then I look at the difference. And whatever the difference in the income is between those two groups of people, I can say that that is the treatment effect. And I can say that there's no selection bias. Why is that? All right, let's go into some more detail. If you remember, selection bias is this expression here. This is our mathematical expression for selection bias. All right. Okay, actually, so this term minus this term is our expression for selection bias. If these two equal each other, then there is no selection bias. Okay, so that's what we're saying here. This expression here says there's no selection bias. What's that mean? Let's go into the details. What we're saying here is that the expected outcome for the treatment group, the expected non-treatment outcome for the treatment group is equal to the expected non-treatment outcome for the control group. If this is true, then we can consider the control group to be a valid counterfactual, and if we have a valid counterfactual, then we can say that we have the treatment effect, the true causal effect of the intervention, the true causal effect of the treatment. All right. Now, we can conclude this. We can say that this is true. We can say that the control group is a valid counterfactual if we have randomly assigned the treatment. All right. Now, in a future lecture, I'll talk about biases that can occur even with randomization. So I will relax this assumption later. Okay, but what I'm going to say right now, we're starting off right now, what I'm saying is that when it's random, the control group is a valid counterfactual. Now, in that later lecture, I will talk about 4 different kinds of biases that can occur even when there's randomization that will threaten the validity or threaten this valid counterfactual argument. But right now, we're going to assume that none of those biases exist. All right, we'll talk about them in a future lecture. And so if none of those biases exist, then we can say that if the treatment is randomly assigned, there is no selection bias. That means the treatment group is the same as the control group on average, which means the control group is a valid counterfactual, which means we have valid treatment effects. That means we can observe the true causal effect of the intervention. All right, so what does this mean? Let's keep going. So when I have randomly assigned the treatment, That means I've randomly selected who gets the treatment and who doesn't. I have what's called I should have what's called statistical independence. Statistical independence means that the treatment group is the same as the control group on average. All right. So this means the treatment assignment is independent of all other variables. It implies that the treatment group is on average the same as the control group. And statistical independence is more likely to hold as the sample size increases. Okay, so randomization will give us statistical independence, which is that the treatment group is the same as the control group on average. Randomization is likely to give us statistical independence when we have a really big sample size. It's not guaranteed when we have a small sample size, but if we have a really big sample size, then randomization will give us statistical independence. All right. So now let's keep going. So random. What do I mean by random? So what I mean by random is that the treatment status is not determined by any other information or data. All right. That means that there's no other information, data, there's no other variable, there's no other factor that determines who gets in the treatment group and who doesn't. Now, if you remember from my discussion of selection bias, what I was saying was that basically the idea behind selection bias is that there is some reason for why the treatment group is different than the control group. There's some reason why the treatment group has the treatment and the control group doesn't have the treatment. If there's any reason at all, then there's a possibility for selection bias. Well, then how does randomization solve it? Randomization solves that problem because when you randomly assign who gets the treatment, there is no reason why they have it. It's entirely independent of all other characteristics. The random assignment means that who has the treatment is not determined by anything else. It's entirely random. All right, so when I say random assignment, that means the treatment status. That means who is in the treatment group, who receives the treatment is random. All right, if I have 1,000 farmers, I randomly select 500 of them, and then those 500, they receive the treatment. The control group, the ones I didn't select, they do not receive the treatment. And if the assignment is random, that means who is in the treatment group is random, then there will be no differences between the treatment group and the control group, and the control group will be a valid counterfactual. All right, so then what do I mean by statistical independence? So that means that there's no statistical difference between the treatment group and the control group on average. All right. Now, what's this issue with sample size? Sample size is the number of observational units. So it might be people or schools or villages, etc. The ability to assume statistical independence after randomization increases with sample size. What do I mean by that? As I'll go over in a little bit, sometimes randomization does not achieve statistical independence when your sample size is too small. If your sample size is really big, then randomization will allow you to achieve statistical independence. Statistical independence is what matters. If you have statistical independence, then your control group is a valid counterfactual. Okay, as long as your sample size is big enough, randomization will achieve statistical independence. If your sample size is too small, then randomization might not succeed at achieving statistical independence. We'll talk more about that in a minute. All right, so what's the intuition behind this? Why does randomization solve the problem? Randomization solves the problem because of what selection bias is. Remember, selection bias is due to some systematic difference between those with and those without the treatment. There's some reason for why the people that have the treatment have the treatment. So let me think of an example. Let's say I ran an NGO, a nonprofit organization, and my goal is to fight malaria. And so I go and I distribute insecticide-treated bed nets. But then when I go to distribute those bed nets, I give it to the people that are most at risk of contracting malaria. All right, so now then if I went and I compared the people that had bed nets to the people that didn't have bed nets, I wouldn't be able to conclude that whatever difference I observe is a result of the bed nets, because the people that have the bed nets are very different than the people that don't have the bed nets. So there could be all kinds of reasons for why the treatment group is different than the control group. All kinds of reasons other than the insecticide-treated bed nets. All right, that would be an example of selection bias. The people that have the treatment are fundamentally or systematically different than those that don't have the treatment. That will create bias, and then we won't be able to identify the causal effect of the intervention, in this case, the insecticide-treated bed nets. Well, how does randomization solve that? What's the intuition? The intuition is that when I randomly determine who gets the bed nets, then there is no systematic difference between the treatment group and the control group. Because randomization, if something is random, that means it is not influenced by anything else. It is not influenced by any other data, any other characteristic. It's not influenced by anything else. And so that would mean that there's no systematic difference between the treatment group and the control group, which would then imply that the control group can be a valid counterfactual because there's no difference between the treatment group and the control group on average. All right? That's the intuition behind why randomization would work. Now, randomization is only going to work if it achieves statistical independence, which it's more likely to do the larger the sample size. Okay. All right, so if we remember from our potential outcomes framework, we estimate the average treatment effect. All right, using this equation. This is our average treatment effect on the treated, our ATT. This is our selection bias. If the selection bias equals 0, then our estimated average treatment effect on the treated will equal the true average treatment effect on the treated. All right, so that means if selection bias is 0, then our estimated average treatment effect on the treated will equal the true average treatment effect on the treated. So the question is, when can we say that selection bias is equal to 0? We can say that selection bias is equal to 0 when we have statistical independence, which is achieved by randomization with a big enough sample size. All right. So the estimated average treatment effect on the treated, ATT hat, is an unbiased estimate of the true ATT when the selection bias is equal to 0. All right. This is what randomization allows us to accomplish. Okay. Now, what does this look like in practice? Let's do an example to get an idea of what randomization looks like in practice. All right, so practical randomization. All right, so this is going to be called a randomized controlled trial, an RCT. This is a controlled experiment in the context of social science research. The treatment is randomly assigned, which allows for causal identification of the treatment effect. All right. If we randomly assign it and we get that statistical independence, we're able to conclude that the selection bias is equal to 0, which means our estimated ATT will be an unbiased estimate of the true ATT. Okay. All right. So what we do to do that is we conduct what's called a randomized controlled trial, which is a controlled experiment where we randomly assign the treatment. All right. An RCT is an experiment in which we randomly assign who gets the treatment. All right. So let's do an example. Let's go to my classic example. The research question is, does fertilizer improve farmers' incomes? Okay. The outcome variable is going to be annual income. The treatment is going to be we're providing fertilizer to farmers. All right. So we want to know the impact. What's the impact of providing fertilizer to farmers on annual income? All right. We're looking for the impact of fertilizer on annual income. So the treatment is the fertilizer. The outcome is the annual income. All right. Practical steps. First, we got to identify a sample population. Then we will determine the level of randomization. I'll talk about that in a minute. Collect the baseline survey, and then randomly assign the treatment. We will randomly assign the treatment. We're going to go through all these steps. Let's go. All right, so let's say we're working in a developing country and we find the following sample. We have a sample population of 10,000 farmers, and they are from 100 villages. All right, so we have a sample of 10,000 farmers from 100 villages. All right. The level of randomization. All right, so now we're going into this in practice. What does it look like to conduct an RCT? What's it look like to randomly assign a treatment? So let's go through it. So the first is we need to determine the level of randomization. The level of randomization is the unit of observation that is randomized. Statistical independence is only going to apply at that level of randomization. All right, so what level of randomization should we choose? What do I mean by that? What I mean is that I can randomize. Remember my sample. I've got 10,000 farmers, 100 villages. I can randomize at the farmer level, or I can randomize at the village level. What does that mean? If I randomize at the farmer level, that means I'm going to take 5,000 farmers, and I'm going to give them the treatment, the intervention. They're going to get the fertilizer. And I'll take the other 5,000 farmers, and I will not give them the fertilizer. So they're the control. All right. So it means I randomly select 5,000 farmers to give fertilizer to, and then the other 5,000 I don't give fertilizer to. So I randomly select 5,000 farmers to be in the treatment group, and 5,000 farmers to be in the control group. All right. That would be randomization at the farmer level. That means I randomly assign farmers to the treatment group and farmers to the control group. I also could randomize at the village level. Randomizing the village level would mean that I'm randomly assigning entire villages to be in the treatment group or the control group. So in that case, that would be I'm going to randomly select 50 villages to receive the treatment and 50 villages to receive the control. That would mean that those 50 treatment villages, all the farmers in those villages receive fertilizer, and then the 50 control villages, all the farmers in those 50 control villages do not receive the fertilizer. All right? That would be randomization at the village level. So the level of randomization refers to what unit of observation I am conducting my randomization at. I can randomly assign farmers, or I can randomly assign villages. All right, now why would I do one or the other? All right, so there's going to be pros and cons of each. What are some pros of farmer level? Well, one advantage of randomizing at the farmer level is oftentimes it's less expensive. It's oftentimes less expensive to randomize at the smallest unit. All right, so in our example, we've got farmers and villages. We can imagine different things. Let's say we were doing an analysis of the impact of textbooks on student performance. Well, we could randomize at the student level, or we could randomize at the school level, or we could randomize at the school district level, or we could randomize at the community level, etc. There's different levels in which we can randomize. All right. And so what are the advantages of randomizing at the lowest level, the smallest level? In our case, the farmer level. What's the advantages of randomizing at the farmer level? One advantage is it's oftentimes the cheapest option. Why is it cheapest? Well, it's because we usually have the largest sample size among that lowest observation. So for example, in our sample in this example, our sample has 10,000 farmers and 100 villages. So we have a huge sample size when it comes to farmers. We have a small sample size when it comes to villages. Okay? And to achieve that strong statistical independence, we want a large sample size, which means that if we randomize at the farmer level, we have a very big sample size. We have 10,000. So I'm kind of talking about this one first. I'm going to talk about this one first. So at that farmer level, we have this big sample size. That's going to mean it's way easier for us to get that statistical independence that we want. It's going to be way easier for us to conclude that the treatment farmers will be the same as the control farmers on average. All right. So a big advantage is that the sample size is bigger. Now, why does that mean that it might be cheaper? Well, remember, everyone in your treatment group needs to receive this intervention. It means you have to buy the fertilizer. That's expensive. That can be expensive, all right? If you randomize at the farmer level, then you might not need to use all 10,000. 10,000 is a huge sample size. You would do just fine using only 2,000. So if you randomize at the farmer level, instead of using all 10,000 farmers, you'll use only 2,000 farmers. Randomly assign 1,000 to the treatment, 1,000 to the control, and all of a sudden you're saving a lot of money. Because you don't need to buy fertilizer for 5,000 farmers, you only need to buy fertilizer for 1,000 farmers. Okay, because 2,000 farmers is a plenty big sample size for an RCT. You don't need to use all 10,000. Okay, so those are the advantages of farmer level. What are the disadvantages of randomizing at the farmer level? One is that we could run into the problem of having spillover effects. In a future lecture, I'm going to go into spillover effects in more detail. But what happens is that if you randomize at the farmer level, you could easily end up with a treatment farmer, it means a farmer that receives the fertilizer, living right next door to a farmer in the control group. That means they don't get the fertilizer. If you have farmers that live right next to each other, one has the treatment, one doesn't, we can easily imagine that somehow the farmer that has the treatment is going to be able to help the farmer that doesn't. Maybe the farmer that has the treatment shares some fertilizer with the farmer that doesn't. Or maybe the farmer that has the fertilizer, they make more money and they share some of their money with the control farmers. All right, this would cause biased results. Even though we've randomized, this would cause biased results. All right, so one of the cons of randomizing at the farmer level is spillover effects. It's that the treatment affects not just the treatment group, but it also affects the control group. All right, that's a downside. The reason that occurs is because when we randomize at the farmer level, it's possible that you will get a treatment farmer and a control farmer that live very close to each other. They interact with each other, and the control farmer can be affected by the fact that the treatment farmer has the intervention. Okay, so that's a con. The other con is that we could have an ethical problem. And that is that let's say that you have farmers that, they live in a village, they live right next door to each other, they interact with each other all the time. One of them gets the intervention, the other one doesn't. That could create social conflicts. That could create social problems. The farmer that doesn't get the fertilizer could be jealous of the farmer that does. It could cause, social tensions. And that raises ethical questions. We don't want to conduct experiments that would, damage the relationships that exist between members of a community. All right, so those are the disadvantages of randomizing at the smallest level. When we randomize at the smallest level, there's these possibilities for spillovers, and there's this possibility for ethical concerns. All right, so then why might I randomize at the village level, or why might I randomize at a higher level? Well, first, let me be really clear. If I randomize at the village level, what I'm saying is that I'm randomly choosing entire villages to get the treatment, and then entire villages to get the control. That means all the eligible farmers in the treatment villages will get the treatment, and then all the farmers in the control village will not get the treatment. Okay. So, what are the advantages of that? Well, the advantages are you reduce the possibility of spillovers, because it's much less likely that farmers in different villages will interact with each other. If you're in a treatment village, it's not likely that you're going to have continuous contact with someone from a control village. These villages might be far apart. So it reduces the chance of spillover effects. For the same reason, it reduces the possibility for ethical problems. The control farmers, the treatment is not causing social conflict between the farmers that get the intervention and then farmers that don't get the intervention. All right, so lower spillover effect risk and lower ethical concerns. All right, what are the cons? Well, the cons are that the sample size is going to be smaller. All right, you only have 100 villages. That means there's only going to be 50 treatment villages and 50 control villages. That's a smaller sample size at your observational unit, at your level of randomization. All right, that means it's going to be harder for you to achieve that statistical independence. All right, the other disadvantage is that it's probably going to be more expensive. The reason is that you're going to have to give fertilizer. I'm going to make a little correction here. Provide fertilizer to 5,000 farmers. You're going to have to give fertilizer. You're going to have to give fertilizer to all 5,000 farmers in the 50 treatment villages. Okay. So because we're randomized at the village level, you need to give the intervention to everyone in the treatment villages. All right? That means you can't we're not reducing the sample size. All right, we can't reduce the sample size. We got to give the intervention to all the farmers in the treatment villages, and so that means it's going to be more expensive. We have to buy more fertilizer. All right, so those are some advantages and disadvantages. Okay, and then you just have to kind of weigh those advantages and disadvantages based on your particular research question. Is it better to randomize at the lowest level or at the highest level? If you think that spillover effects are not going to happen and you're not concerned about ethical problems arising, then you might choose the lowest level. If you're very concerned about spillover effects and ethical concerns, then you might choose the higher level, the village level. Okay. Okay, so we randomly assign. So what we're going to do, once we've picked our level of randomization, then what we're going to do is we're going to randomly assign half of the sample to the treatment group, and the other half will go into the control group. That means half of the sample will receive the intervention, and the other half will not. And if our sample size is large enough, we'll be able to achieve statistical independence, and we'll be able to conclude that our selection bias is equal to 0. That means our treatment group is the same as our control group on average. However, when the sample is too small, the random assignment can fail to create equivalent means for the treatment group and control group. That means it's possible. If our sample size is too small, then we will not be able to eliminate selection bias. All right. I'll come back to this in a minute. So let's just make it clear. Let's say we've got 2,000 farmers. What we do is we randomly select 1,000 farmers to be in the treatment group and 1,000 farmers to be in the control group. What would that look like? All right. So let's say I've got my mock sample here. I need to make a little edit here. So I've got 6 villages. I have village 1, 2, 3, 4, 5, 6. All right, and all those villages have some farmers in them, my happy orange farmers. All right, and so if we randomize, that means we randomly select who gets the treatment and who doesn't. All right, so now we're randomizing here, and so some farmers are going to get the treatment. All these T farmers are going to get the treatment. All right, and then the C farmers are going to get the control. So the C farmers are going to get the control. All right, so this is our randomization. We've just randomly picked who gets the treatment and who gets the control. You'll notice that in some of the villages, you're going to have treatment and control individuals. So in village 1, 2, oh, I got to correct this again. All right, in village 1, 2, 5, and 6, you have some treatment farmers and some control farmers. All right. In village 3 and 4, in village 3 you have only treatment, in village 4 you have only control. Okay, this can happen. We're just randomly, we're conducting our randomization at the farmer level. Now I mentioned before that you're going to have a possibility for spillover effects when you have a treatment farmer in the same village as a control farmer. So when you have treatment and control individuals that are really close to each other, you have a higher chance of there being a spillover effect. All right, so that's what I'm talking about here. All right, so individual level randomization or farmer level randomization. We also could do village level randomization. That's where we randomly select half of the villages to be in the treatment group and half of the villages to be in the control group. All right, so in this case, village 1, 3, and 5 were randomly selected to be in the treatment group. That means all the farmers in the treatment villages receive the treatment. All right, so all the farmers in the treatment villages receive the treatment. All right, and then villages 2, 4, and 6 were randomly assigned to the control group. That means all the farmers in the control villages receive the control. All right, so now what we end up doing is comparing the treatment villages to the control villages to observe our treatment effect. All right, so it's village level randomization. Okay, so with that, that kind of concludes our overview of choosing the level of randomization, and then what does it look like when we implement it. If we do individual level randomization, then what we do is we're just randomly selecting individuals or farmers and assigning the treatment status. If we do village level or some higher observational unit, then we randomly assign that higher observational unit, so village in this case, to the treatment group and the control group. Okay. Now what I want to talk about is collecting a baseline survey and then what we're able to do using a baseline survey to confirm that our randomization achieves statistical independence. So let me explain that. All right, baseline survey. So a baseline survey is a survey taken before a treatment is implemented. So a baseline measure of outcome variables and covariates. This allows the researcher to ensure that we have successful randomization ex ante. It allows us to stratify the sample across covariates. It allows us to control for time differences if necessary. I'm going to talk about stratification in a minute. All right. So in theory, because randomization should establish independence, baseline surveys are unnecessary. However, if our sample size is too small, a baseline survey will be highly valuable. All right, what do I mean by a baseline survey? When we do these analyses, what we do is we go and we collect survey data on the individuals that are in our sample. We collect data on the individuals in our sample, and we use that data to analyze the effect of our treatment. We collect data on our outcome variable, and we collect data on a bunch of other variables, individual characteristics, all kinds of things. We'll get more into that in a minute. A baseline survey is just when we collect a survey before we implement the intervention. All right. Now I'm going to talk about why that's so important, why that's helpful. All right. Now, as I mentioned before, when we randomize, if our sample size is big enough, then our randomization will achieve that important statistical independence. But sometimes our randomization fails to create statistical independence. This can occur when the sample size is too small, or when there's just too much variation in the sample. That means we've got a sample of individuals and they're just very different from each other. Okay? And then, lastly, it can just occur by chance. Just by chance, randomization can fail to achieve statistical independence. But that's very, very unlikely when our sample size is big. When our sample size is small, then it's much more likely for our randomization to not create statistical independence. All right. So, basically what I'm saying here is that randomization should create statistical independence, but that's only as long as our sample size is big enough. And in practice, randomization might not always create statistical independence because we may not always have really big sample sizes. All right, so then basically what's going on here is that we just by randomizing, we don't necessarily know whether or not statistical independence is achieved. And so there's something that we are always going to do when we analyze data from a randomization, from a randomized experiment, from an RCT. What we're always going to do is we're going to do something called a test for balance. Basically, we're going to perform a test to see whether or not our randomization achieved statistical independence. All right, and this is called a test for balance. We conduct a test for balance, or a balancing test, to confirm whether or not our randomization achieved statistical independence. All right, that's why we do a test for balance. So let me go into that. A test for balance. So we say that two groups balance, or a variable balances, when two groups are statistically identical on average. Okay, so we want our treatment group and our control group to balance. That means we want them to be the same on average. If my treatment group and my control group, if they balance, that means that they have statistical independence. That means our control group is a valid counterfactual. All right, so we want our treatment group and our control group to balance. And so now what we do then is we conduct a test for balance. We test to see whether or not our treatment group is, in fact, the same as our control group on average. All right, so we conduct a test for balance. What's a test for balance? So what we use mean t-tests for covariates, and we test to see whether or not variables are the same for the treatment group and the control group. We know that we have statistical independence if there are no statistically significant differences between our treatment group and our control group on average. And we use the t-test to show whether or not we have significant differences. All right. So let me get really practical here. This is what we do when I say a test for balance. A test for balance is, what we do is we take a bunch of variables from our data set. So a bunch of characteristics of the individuals in our sample. We take a bunch of their characteristics, a bunch of variables from our data set, and we conduct what's called a mean t-test to see if those variables are different between the treatment group and the control group. All right, let me be even more specific. What I do is I take a bunch of variables or characteristics from my sample population, and I compare the average values of those variables between the treatment group and the control group. All right, so in our particular example, what we're doing is we have a sample of 10,000 farmers, and we want to look at the impact of fertilizer on those farmers' incomes. And so now what we're saying is, let's imagine that we've collected a baseline survey. So that means we have information on all 10,000 farmers before the intervention is implemented. Okay, so we have information on these farmers. We know their incomes. We know how much land they have. We know how many years of education they have. We know their age. We know their gender. We know how far away they live from the market. We know all kinds of things about our 10,000 farmers. From our baseline survey, there's been no intervention yet. We've taken a baseline survey, so we know a bunch of things about our sample. We know a bunch of information about the farmers that are in our sample population. In this case, I'm saying that we know their incomes, we know how much land they have, etc. So what we will do is we'll take all that information, we will randomly assign half of those farmers to the treatment group and half of them to the control group. All right, but before we give any of them the treatment, we're going to compare our treatment group to our control group. We're going to compare our treatment group to the control group. What we want What we want to see is that our treatment group is the same as our control group on average. We want to see if our treatment group is the same as our control group on average. If they're the same, then we can say, all right, there's statistical independence. Our randomization was successful. We have achieved statistical independence. Now we can go ahead and implement our experiment, and we'll be able to conclude from that experiment that we have no selection bias and we'll have a causal effect. We'll be able to determine our causal effect. Okay, so what we do is then we assign people to the treatment group and we assign people to the control group. But before we go and give them the intervention, we look and we compare the average values for a bunch of these characteristics. All right? So let's go through the examples. Let's say we have information on all of our farmers. We have their agricultural incomes. Okay? We've randomly assigned half of them to the treatment group and half of them to the control. And now we're going to compare. What's the income for the treatment group and what's the income for the control group? What's the average income for the treatment group? What's the average income for the control group? All right, so we calculate it. The average income for the treatment group in this example is $12,100, and the average income for the control group is $12,050. All right, and then we calculate the difference. The difference between them is 50. There's a 50 Ghana City difference between the treatment group on average and the control group on average. And we conduct a t-test to determine whether or not this difference of 50, is statistically significant or not. We would say that the treatment group and the control group balance across for the incomes variable. They balance for the income variable if the difference is not statistically significant. If the difference is not statistically significant, then we can conclude that there actually is no difference. There's actually no difference between the treatment group and the control group on average for the income variable. All right, we'll do it again. Let's do land holdings. It's how many acres of land the farmers have. So on average, the average number of acres that the farmers own, that the treatment farmers own, is 8.5 acres. The average acres that the control farmers own is 9 acres. That's a difference of 0.5 acres. So then we'll use a t-test to determine whether or not this difference is statistically significant. If it's not statistically significant, then we will conclude that there is actually no difference between the treatment group and the control group. And at that point, we will say that the treatment group balances with the control group for the landholding variable. It means there's no difference on average between the treatment group and the control group if it's statistically insignificant, if it's not significant. All right. When we're doing these balancing tests, we want our randomization to achieve statistical independence. Statistical independence means that there is no difference between the treatment group and the control group on average. That means I want to see these differences to be insignificant, not significant. I do not want to see a statistically significant difference between these averages. All right, I do not want to see a significant difference between these averages. Okay, so we keep going. Education. All right, education level. All right, so the average education level for the treatment group is 5.6. The average education level for the control group is 6.1. It's a difference of 0.5. So a difference of 0.5 years of education between the treatment and control group. The question is this difference significant? If it's significant, that means our treatment group is different than our control group. If it's insignificant, that means that our treatment group is the same as our control group on average for the education variable. Now in this table, I'm labeling statistical significance using stars. All right. So if there's a star, that means that there's some level of statistical independence. 3 stars means it's significant at the 1% level. 2 stars means it's significant at the 5% level. 1 star means it's significant at the 10% level. Okay, so these 3 are statistically insignificant. That means our treatment group and our control group balance across incomes, landholding, and education. What about age? The average age of the treatment group is 45. The average age of the control group is 43. This means that there's a statistic that means that there's a difference of 2, but it's not statistically significant, which implies that our treatment group is the same as our control group on average for the age variable. All right, same thing for gender. They are the same on average for gender. Okay, but now we come to distance to market. We're saying the average distance to market in the treatment group is 3.2. The average distance to market for the control group is 6.3. There's a difference of 3.5, and I'm saying that's statistically significant. That means our treatment group is not the same as our control group on average with respect to the distance to market variable. All right, so let me summarize. If the sample size is big enough, we would expect that randomization would result in there being no differences between the treatment and control group, just like we see in the first 5 variables. In the first 5 variables, we see no difference between the treatment and control group. That's what we would expect to find for all the variables if we had a big enough sample size and randomization achieved statistical independence. But what we see here, all right, the stars indicate statistical significance. All right, the significance is determined by this mean t-test. See my lecture using Stata to go into the details on how to perform this. Okay. So what we want is that we want to compare the treatment group and the control group for a whole bunch of different variables. We want to look at a bunch of different variables. And if we look at a whole bunch of different variables and there's no difference between the treatment group and the control group on average for a whole bunch of different variables, maybe 10 to 20 variables, then we would say we have evidence of statistical independence. If our treatment group is the same as our control group on average for a whole bunch of variables, we would say that that gives us evidence that we have achieved statistical independence. Remember, statistical independence is where our treatment group is the same as our control group on average. And so the way that we test that is we do this mean t-test for a whole bunch of different variables, and if we find that they're not statistically significant, then that would mean our treatment group is the same as our control group on average. That validates statistical independence. However, if we do this balancing test, we do all these tests, we compare the average between the treatment group and the control group for a whole bunch of different variables, and we find that some of them are highly significant, that would imply that our treatment group is not the same as our control group on average, which would mean that our samples don't balance and our randomization did not achieve statistical independence. All right, that might imply that our sample size is too small. It might imply that there's just a lot of variation in our data set, in our sample. It also could just happen by chance, but it's a lot less likely to happen by chance when we have a really big data set. When we have a small data set, it's much more likely to happen. Okay. All right, so balancing in general. So balance across as many variables as possible. The means should be insignificantly different for most. All right. So if we want to say that we have statistical independence, then we want to say that there's no statistically significant difference between the treatment group and the control group. All right. That means we want to do these balancing tests. We want to do these mean t-tests for a whole bunch of variables. And we want to find that they're insignificant. All right. If we find that they're significant, that means that that we don't have statistical independence. All right. But now, what's the threshold? When do we say that there's too much significance? All right, here's the threshold. If 10% of the variable, all right, so just by chance, 10% of the variables will be significantly different at a 10% level. And so if we have more than 10% of our variables are significantly different at the 10% level, then we would say that our samples are not well balanced. That means that if 1 out of 10 variables is significant, what that means is that just by chance, 1 out of 10 variables will be significant at the 10% level. And so, if we have more than 1 out of 10 variables that are significant at the 10% level, then we would conclude that our sample is not well balanced. Or if we have, one variable, if we have 1 out of 10 variables that are significant at more than the 10% level, so let's say we had one out of 10 variables was significant at the 5% level, that would mean that it's not well balanced. Okay. All right. So now we can do this balancing test. We can do it ex ante or we can do it ex post. What does that mean? Ex ante means we're doing it before we implement our intervention. All right, if we balance before we implement our intervention, that means before we conduct our RCT, before we give out our intervention. If we balance before the intervention, we would do it to ensure that our assignment, our random assignment, achieves statistical independence. We would use it to ensure that our treatment group and our control group balance. Okay. We could also do a balancing test ex post. That means that we can use a balancing test after the RCT has been implemented to confirm that the randomization produced a truly random assignment. But when we do it ex post, it'll be a little bit different than when we do it ex ante. If we conduct a balancing test ex post, then we should only include variables that can be safely assumed to not be impacted by the treatment. We would only do this if we did not have a baseline survey. Okay. In your first assignment, you are doing a balancing test ex ante. In your second assignment, you do a balancing test ex post. That means after the intervention has been implemented. So there's some differences between doing a balancing test ex ante and a balancing test ex post. I will now explain that. All right. So let's say that we're going to do a balancing test ex ante. That means we're doing it before we implement the intervention. If we do it before we implement the intervention, then we're going to include as many variables as possible. And we are especially going to include the outcome variable. We definitely want to include in our balancing test the outcome variable. It is essential that we include the outcome variable. That means it's essential that we include, in this case, if you remember, this example, we're looking at the impact of fertilizer on incomes. So it is absolutely essential that if we do our balancing test ex ante, that means we do our balancing test before we implement the intervention. It is absolutely essential that we include the outcome variable in our balancing test. It's absolutely essential. And the reason it's essential is because we want to be sure that our treatment group is the same as our control group on average for our outcome variable. All right, because after we implement the intervention, we're going to compare our treatment group. We're going to compare our outcome variable between the treatment group and the control group. And we want to be able to attribute whatever difference we see to the effect of the treatment. And so we absolutely need our treatment and control group to balance for the outcome variable. That means we want our treatment group to be the same as our control group on average for the outcome variable before we implement the intervention. All right, that's absolutely essential. All right, but let's say we do the balancing test after the implementation. So let's say we don't have a baseline survey. So that means we don't know what our sample was like before the intervention. We only have data after the intervention. All right, so we only have data after the implementation. How does that change our balancing test? How does that change our balancing test? If we do a balancing test after the implementation, we're doing the balancing test for the same reason. We want to know that our treatment group is the same as our control group on average. The problem is, if we do a balancing test after the implementation, it's possible that some of the variables have been affected by the treatment, right? Because we're doing it after the implementation. That means we're doing it after the treatment group has received the intervention. Which means that the intervention may have affected some of these variables. They may have affected incomes or land holdings, etc. And so if we're doing a balancing test, all right, remember, we're doing the balancing test to see whether or not our treatment group is the same as our control group on average. All right, we can't include variables that could have been affected by the treatment. And so if we're doing our balancing test ex post, we're doing it after, that means we will not include variables that we think may be affected by the treatment. So if we go through this list of variables, we know our incomes are probably going to be affected by the treatment. So we can't include that in our balancing test. Land holdings, they might be affected by the treatment. You know, if you get fertilizer, maybe that's going to increase your yields, and so you go and you buy more land because now you have fertilizer. All right, so land holdings might be affected by the treatment, by the intervention. All right, so we cannot include those. Education level, usually we're measuring the education level of the household head or the education level of the farmer. It's very unlikely that when the farmer gets fertilizer, they're going to go back to school. When they get fertilizer, they're going to work even harder on their farm. All right, so they're not going back to school. This one's not going to change. The age is not going to change. The gender is not going to change. Where the farmer lives, the distance to the market is probably not going to change. So we can balance across these variables. We will not balance across variables that could have been affected by the treatment. All right, ex post, after the implementation, we do not balance across variables that could have been affected by the treatment. All right, why? Why don't we balance across those variables? All right, we have to remember, why are we doing the balancing test? We're doing the balancing test to see whether or not our treatment group is the same as our control group on average. We want our treatment group to be the same as our control group on average. Okay. We want our treatment group to be the same as the control group on average before the intervention, so that we can conclude that any observed difference that we see in our outcome variable is the result of the intervention, and not the result of some systematic difference between our treatment group and our control group. Okay, so then we can't include variables that would be affected by the treatment in our balancing test, because if we observed a difference, let's say we included this, and let's say we observed a difference between agricultural incomes between the treatment group and the control group. Let's say this 50 was significant. If we observed a difference, we wouldn't know whether or not that is a result of the treatment or whether or not that's the result of the treatment group being systematically different from the control group. Basically, we wouldn't be able to conclude anything about these variables because they may have been affected by the treatment. All right, so we don't include them in our balancing test. We only include variables that wouldn't be affected by the treatment in our balancing test if we are conducting our balancing test after the implementation of the intervention. Okay. So if we do that and we see that these variables that are not affected by the treatment, if we see that these variables which are not affected by the treatment, if we see that they all balance, that means they're all statistically insignificant, that supports our claim that our randomization achieved statistical independence. If we find that these variables, that there's a statistically significant difference between them, that would undermine our argument for statistical independence. That would show us that we don't have statistical independence. All right, so that's why we do the balancing ex post. Now, if let's say we conducted this balancing test and we find that all of these are insignificant, that would mean that we have provided evidence that we have achieved statistical independence, which would imply that any difference that we observe between our treatment group and our control group is a result of any observed difference in our outcome variable between our treatment group and our control group is a result of the intervention, not a result of some other factor. Okay? If we find that some of these variables are significant, more than the threshold, then we would conclude that we don't have statistical independence and we're not necessarily able to conclude that any observed difference in our outcome variable between the treatment group and the control group is a result of the treatment, is a result of the intervention. In this case, we find that 1 out of 4 variables is significant at the 1% level. And so if we were looking at this, we would say this sample does not balance, we do not have statistical independence, and we cannot conclude that there's no selection bias. That means our estimate of the treatment effect will be biased in this case. All right. So we balance ex post. We use this to determine if the treatment assignment was successful. If the sample is not balanced, we have to acknowledge this in the paper. We will then include the unbalanced variables as independent variables in the regression model. And we might include other regression approaches that we'll talk about later in the course. All right, that's how we would solve it, basically. If we find that the sample doesn't balance, we have to try to solve it somehow. We would acknowledge it in our research paper. We would include the unbalanced variables as independent variables in the regression model. And we would consider using some other approaches that we'll talk about later in the course. All right. Now, let's go back to thinking about balancing ex ante. If we balance ex ante, that means we have a baseline survey. That means we know things about our sample before we implement the intervention. All right, so let's go back to that context. We have a baseline survey, and we have conducted a balancing test before implementing the intervention. All right, we've taken our data, we've taken our sample, we've randomly assigned half of them to the treatment, half of them to the control, and now we've checked for balance. We've run our balancing test. We've run these mean t-tests between the treatment group and the control group for a whole bunch of variables, 15 to 20 variables, let's say, all right, using baseline data. If that sample achieves statistical independence, that means we do the balancing test, 15 to 20 variables, and we find that no more than 1 out of 10 is significant at the 10% level. Then we would say, great, we have achieved statistical independence. All right. If we've achieved statistical independence, then we're fine. We move forward, we implement our intervention, we give the treatment to all the treatment individuals, and we don't give the treatment to all the control individuals. Okay, but let's say we have a relatively small sample size, and so we do our randomization, and they don't balance. We do our randomization, and more than 1 out of 10 variables is significant at the 10% level. In that case, our samples don't balance. Our treatment group is not the same as our control group on average. If that's the case, what we will do is we will re-randomize. We'll randomize again. We'll pick a new random sample. We will repeat the randomization until our treatment group is the same as our control group on average. Then we will implement the intervention. You do this in assignment 1, in the first assignment. Okay, so that completes our discussion of randomization and balancing tests, and I've illustrated the difference between balancing ex ante, which you do in assignment 1, and balancing ex post, which you do in assignment 2. All right, now let me add some more to this. Let me introduce this concept of stratification. Okay, stratification. Stratification is something that we can do while we implement our randomization. What stratification is stratification is a procedure where we guarantee that the treatment group and the control group are going to balance for a specifically determined variable. All right. So what stratification does is, what happens is I pick some variable, some characteristic, and then I will guarantee that my treatment group and my control group are going to balance across that variable. All right. So let me be more clear. All right, so what we do to stratify is first we choose a variable or a set of variables in advance of the randomization. These variables should be variables that we believe will have a strong impact or relationship with the outcome variable. All right. What we do then is we stratify the data into each of these categories, into each category by these variables, and then we randomly assign the treatment status within each strata. All right, I'm going to make that more clear in just a minute. Okay, but let's use one quick example here. So let's say we're stratifying by gender. Stratification by gender. What that means is before I randomly assign the treatment assignment, before I take my farmers and I assign them to the treatment group or the control group, before I do that, what I do is I separate my sample into male farmers and female farmers. Then, amongst all the male farmers, I will randomly assign half of them to the treatment group and half of them to the control. And then, within all the female farmers, I will randomly assign half to the treatment and half to the control. That would be stratification. Let me give you real quick. I'm going to give you another example in just a second to illustrate it, but let me specify when we stratify. All right. Why do we stratify? When would we do that? We stratify when there are covariates that are going to have significant impact on the outcome variable. Okay, that means when there's some variable, some characteristic that we think will have significant impact on the outcome variable. All right, when there are covariates that will be highly correlated with many other important covariates. All right, real quick, a covariate. A covariate is just an independent variable in the regression model other than the treatment. All right, so when I say a covariate, that means some variable, some characteristic of our sample data. All right, so when there are covariates, when there's some characteristic that we think will have a significant impact on the outcome variable. Okay, or when there are covariates that will be highly correlated with many other important covariates. All right. Or when there are important heterogeneous treatment effects that we want to investigate. When I say heterogeneous treatment effect, I mean subgroup analysis. I might add that here. When we want to do a subgroup analysis. Okay. And this is particularly important when we have small sample sizes or big variations in the sample data. All right, so let me illustrate what I mean by stratification. So let's say I have 2,000 farmers, all right, and 1,200 of those farmers live in region A, and 800 farmers live in region B. All right, let's also say that these regions are very different from each other. That means the farmers that live in region A are very different than the farmers that live in region B. This would justify the idea that we would stratify by region. And so what that means, what stratifying by region means, is we're going to separate our sample into two subgroups. The region A subgroup and the region B subgroup. All right. The region A subgroup has 1,200 farmers. The region B subgroup has 800 farmers. Okay. Now, within the 1,200 farmers in region A, we will randomly assign 600 to the treatment and 600 to the control. Within the 800 farmers in region B, we will randomly assign 400 to the treatment and 400 to the control. All right. So basically what we're doing here is we're randomly assigning the treatment within the two different regions. So we would say that these are the strata. So region A, that's strata 1. Region B is strata 2. And so we're randomly assigning the treatment within the strata. That means we're randomly assigning the treatment farmers and the control farmers within region A, and then we're randomly assigning the treatment farmers and the control farmers within region B. Okay, so let's look at what that looks like. So randomization without stratification. I had this slide before. Randomization without stratification. When you randomize without stratification, it is possible that you're going to get some villages that have treatment and control groups. All right, that's village 1, 2, 5, and 6. All right. But it's also possible that you could get villages that have only treatment or only control. So village 3 has only treatment, village 4 has only control. All right. This is a problem if we think that villages are really different from each other. If the farmers in these different villages are very different from each other, let's say if village 1 is really different from village 2, and village 3 is really different from village 4, then we don't want village 3 to have all treatment farmers and village 4 to have all control farmers. Because if we were to compare village 3 to village 4, if we were to compare these farmers to these farmers, we would be comparing farmers that are very different from each other, which would mean that we would have selection bias. Okay, and so if we think that these villages are very different from each other, then we really want to avoid the scenario in which one village has all treatment and another village has all control. So what we would do is we would stratify. So in this case, we're stratifying by village. So stratification by village. That makes sure that each village has an equal number of treatment and control. The random assignment is done within the village. So that means within each village, I'm randomly assigning who gets the treatment and who gets the control. This guarantees that within each village, there's an equal number of treatment farmers and control farmers. What that does is it guarantees that even if there's big differences between villages, that we're always going to have a good comparison group. We're always going to have a good control group for every treatment group. That means our treatment group is always going to have a good control to compare it to. If village 3 is very different from village 4, that's okay. That's okay because we've got an equal number of treatment farmers in village 3 as we have control farmers in village 3. That means we can compare these farmers to these farmers and identify the treatment effect within the village. All right, so when we stratify, basically what we're doing is we're creating a whole bunch of mini RCTs, mini experiments. Every village has its own mini experiment, which allows us to identify the treatment effect within each village by comparing the treatment farmers to the control farmers within the villages. All right. All right, I think I'm going to end this video here, actually, and I'm going to create another video where I talk about how we analyze the data from an RCT. All right, I'm just going to split this up because I think the lecture is getting a little long. All right, so this concludes my initial introduction to randomization, RCTs, level of randomization, stratification, and balancing tests. All right, thank you very much, and I hope you are having a great day.